Okay, welcome. Happy March. And today I'm going to discuss how things get complicated in the world. Now, that is a problem in modern physics because we've arrived at extraordinarily simple and powerful uh, models, both of the fundamental laws and of the starting condition of the universe, which I'll very quickly indicate. And then the question is, it becomes well posed, how did you get from these simple starting points, conceptual and physical, to the world that we see around us, which is, of course, very far from simple. So that'll be my subject today. So to set the stage, let me first document the fact that we have simple laws and simple starting conditions to get the laws started on some started in action. So famously, the content of the standard model of particle physics, understood also to include gravity. So it's really the description of all known experimental phenomena can be written in an honest way, very comfortably on the front of a t-shirt. And here it is, the core theory. You can actually order this t-shirt online. I won't explicate the meaning of all the different symbols, but this is really an honest representation of our fundamental laws of physics. It's got quantum mechanics in it. It's got a general relativity, space-time. It's got our theories of the strong electromagnetic and weak interactions. It's got the theory of electrons, and even it's got the Higgs particle, which in the context of this model is important for giving some particles mass. And as far now, to spell it out fully, you have to give numerical values to these y's, and actually there are 3 different terms like this for the strong electromagnetic and weak interactions. But basically, this is an honest representation of the fundamental laws of physics. And it shows how far we've fulfilled the reductionist ideal of explaining the basic operating system of the world in terms of elemental, tiny little things, a fairly small number of them, with very, very definite, simple properties. The objective measure of that, I would say, is that the equations of the core theory, that is, if you spell out the consequences of what's written on that t-shirt, you can write them in the form of a computer program that wouldn't be very complicated. It would, I estimated it would take about 150 lines of Mathematica code to write the operating system of the world, and you could probably boil that down further if you work in a lower level language. So the operating system of the world is much simpler than the operating system of your computer, or a program like Word. And if you took that program and gave it enough time on any computer, any universal Turing machine, which all modern computers are, and gave them enough time, they would output the periodic table, the chemistry, material science, everything. All those phenomena are, we believe, with very good reasons, consequences of those laws that you can write on a t-shirt and embody in a short computer program without ambiguity. So this is a remarkable development that all came together really in the 20th century, and to me it's one of the pinnacles of human achievement for all time. Now, so this program would give you, as I said, the kind of the inventory of the world in terms of which chemicals exist, which kinds of materials you could make from them, but it wouldn't give you the world as it is. It wouldn't tell you exactly what actually does exist out there. We need, in formal language, these equations are equations for how things change in time. If you want to, so they need something to start with. You need to say what the state of the world is at one time, and then these equations will tell you what it is at future times. In principle, it will also tell you what they are at past times, but usually. But you need to know what it is at some time in order to get the whole system cranking. And here it is. So we have a simple, in this technical sense, that it can be programmed into a computer with a modest program. It's not simple if you actually, as a human being, want to use it. You have to go to graduate school and learn all kinds of techniques to work with it intelligently, but it's simple in the sense that it's the actual algorithm could be specified concretely and briefly. So what do they get to work on? What is that? And that is also simple, but as I'll show you, it's very strange in a very particular way, and the strangeness is what leads to the whole evolution of the universe, the whole emergence of complexity in the universe. So the conventional Big Bang initial conditions, which are the basis of modern physical cosmology, can also be stated very, very briefly. This is a super brief version in English. To spell it out in terms of equations can also be done briefly, but I haven't got the t-shirt version of that. But the physical picture, though, is very clear and unambiguous. It's that in the very early moments of the universe, we have a starting condition that can be specified very simply. That is that matter is in equilibrium at an extremely high temperature. So you have a really hot gas of all the things that appeared in that core theory. When you go to high enough temperature, the ambient energy is enough to start producing electrons together with the anti-electrons, and all the different kinds of quarks together with their anti-quarks, many photons. All of those are produced in equilibrium at high temperature, so you don't have to specify how much of each thing there is, because there's a dynamic equilibrium that tells you that. And the other condition is that space is very nearly homogeneous and isotropic. And harmonizing these two means that not only is matter in equilibrium, but sort of locally, but also globally, the temperature is the same everywhere. So it's in this sort of more powerful version of equilibrium that's globally enforced. So it's the matter as well as space is homogeneous and isotropic. That means, if you think about it though, that gravity is way out of equilibrium. Gravity does not want things to be uniformly distributed. So gravity is way out of equilibrium. And that's the strangeness of this starting point. And if not for very compelling empirical evidence, this starting point would be hard to believe. But the Big Bang picture is very, very well documented in many ways by now. I won't, of course, have time to go through that, but I hope you've been exposed to it. If not, you can easily find some documentation on the internet or in a library. So, since gravity is not in equilibrium, gravity wants things to clump, but they start out very uniform. That's unstable. There's a gravitational instability, and that's the straw that stirs the drink that takes these simple laws and simple initial conditions and makes it complicated, ultimately. So the subsequent history of the universe at low resolution, so to speak, on cosmic scales, is dominated by the struggle of gravity to get back into equilibrium from this strange starting point. Simple but strange starting point. So this is what gravitational instability is, in a little more pictorially. That is that if you start with a distribution of density where some regions are more dense than others, those more dense regions will exert stronger gravitational attraction and become even more overdense and suck matter out of the less dense regions. And that keeps going. It's obvious. It's a runaway instability. So this is how you, in our standard model of cosmology, start with small fluctuations from perfect uniformity. You can look back at the condition of matter in the universe at, it says redshift equals 1100. That corresponds to about 100,000 years after the Big Bang, when the universe first became transparent to photons. Okay, before that, it's so hot that the photons interact with things and can't move very far. At this point, the photons are able to travel very long distances through the universe, as they do today. The universe is transparent to photons. That first happened around z equals 1100 or 100,000 years after the Big Bang, when matter got sufficiently cold and electrically neutral that photons could penetrate. And those photons redshifted by a factor of 1,000. So having their wavelength stretched by 1,000, are now visible as the microwave background radiation, the famous cosmic microwave background. And that gives us a snapshot. Looking at the microwave sky gives us a snapshot of how homogeneous the universe was at that time. Now, if you look at that picture, it doesn't look very homogeneous, but what you have to realize is that in that picture, here's a bigger version of it, the density contrast has been turned up by 10,000. So the actual, or 100,000, somewhere in between those, depending on the color scheme, of course, is arbitrary. But if you actually looked at a picture of the microwave sky, it would be completely uniform to appearance. You have to turn up the density contrast enormously in order to see anything at all. Okay, so let's go back to that. And then you follow out the basic equations given in that on that T-shirt with a certain recipe for what the matter is. Okay, it's not quite enough to say that it was in thermal equilibrium. You also have to say how much dark matter there was compared to ordinary baryonic matter, how much dark energy, and well, this one just tells you about the age of the universe. So this one is sort of a parameter about today, not the early universe, and this is just the sum of those three. So we need a remarkably small number of parameters: the dark matter density, the dark energy density, and the ordinary matter density, and that's enough to specify uniquely pretty much how things evolve. You have to, as I mentioned before, I think you have to also assume the dark matter is produced cold. But if you do that, then you get something that looks a lot like the present day distribution of matter in the universe. Just run the equations, and that's what you get. So this is the standard model of structure formation. It all comes about from these tiny seeds, seed contrast, which are measured, observed through gravitational instability. Here's a little more about the ingredients and some of the frontiers of ideas about what the dark matter is. Maybe you need to modify gravity. I don't buy this one, but inflation might be responsible for the nature of those initial slight deviations from complete uniformity, and these are the standard ingredients of cosmology. This is saying things start out very, very uniform. This is the kind of matter we know about in great detail. Ordinary, sometimes called ordinary or normal matter, and then we have the theory of gravity and the other equations that go on the T-shirt. So there are material ingredients and equations that go into it. And one more thing I wanted to say about this, which is extraordinary, is that in models of the very, very early universe, which are still somewhat speculative, so-called inflationary universe, these fluctuations can be interpreted as not kind of arbitrary things that you put in to agree with observations, but as quantum fluctuations that get blown up, quantum fluctuations in energy density, similar to what I think I showed you that picture of the fluctuating quantum fields. This is just that blown up by inflation, so that the normally very short distance scales where you have quantum fluctuations actually make a big impact on the universe as a whole. Okay, so that's how gravitational instabilities takes you from by simple equations and simple initial conditions, starts to give you inhomogeneous distributions and starts to complicate things. But to get to even a broad brush description of the world that we see around us and are part of, we need a couple more important things to happen. One is we need stars to light up, because they give us a user-friendly form of energy that can drive complex chemistry and ultimately life. So the key to that can also be understood in a profound way on the basis of the physics we know, and this Big Bang picture of what the equations get to work on. They show that we had equilibrium at extremely high temperatures, but as the universe expands and cools, the equilibrium is harder and harder to maintain. Okay, the particles see each other less because they're moving more slowly, and the universe is getting bigger. So eventually they stop interacting. They freeze out. We saw how photons freeze out, but other things freeze out too. And in particular, nuclear reactions that would ideally burn all the protons into iron nuclei, which are the most stable nuclei, don't get to run to completion because the universe is expanding and the different protons can't find each other, and it's even more disadvantageous because protons can't directly get to become iron nuclei, because iron nuclei contain an equal mixture of protons and neutrons. You have to have weak interactions, which are very slow, in order to have that happen. So even if the universe was not expanding so fast, I mean, it's not a close thing. The burning is nowhere near complete. In fact, the only nuclei that get produced coming out of the universe are, to a first approximation, protons, that is hydrogen nuclei, and helium-4 nuclei. And you have also tiny admixtures of deuterium, which is proton and a neutron, and lithium-7, which is, if I remember correctly, is 3 protons and 4 neutrons, and helium-3, which is 2 protons and 1 neutron, and that's it. And no other nuclei get produced significantly coming out of the Big Bang. All the other ones get produced later when stars bring nuclei together and are able to cook them, because the nuclei, it's much more, it becomes very dense again, and in the center of the star, the collapse is only halted because things get very hot, the nuclei start to combine, and the nuclear burning continues. It's very remarkable and absolutely crucial to the existence of life that we know it, that stars burn incredibly slowly. The time scale for strong interactions is basically, the natural time scale is something like 10 to the minus 24th seconds. So strong interactions happen very, very fast. Electromagnetic interactions typically occur 100 to 1,000 times slower, still very, very fast. Weak interactions, however, take a much, much longer time. And that's the key. In fact, it's exactly what I mentioned to you before. Well, it's 2 things. First of all, to make hydrogen go into helium, you need to take just protons and turn half of them into neutrons. So that involves a weak interaction process and is very, very slow. And that's what helps stars to burn very, very slowly compared to sort of the natural nuclear timescales. And thank goodness for that. Otherwise, the history of life would be very, very short. The other thing that inhibits fast cooking is that once you get nuclei with a large electric charge, it becomes hard for them to come together because of electrical repulsion. If they could come together, close enough, the strong interaction would make that favorable for them to combine. But they have to get there, they have to have a lot of energy, and that doesn't occur until late in the evolution of the star after this more modest temperature process runs out. So you have this is what happens during the so-called main sequence evolution of stars, which is the longest period of their evolution, and subsequent periods when they run out of the hydrogen and start to burn other things, go at higher temperatures to happen at all. But once they happen at higher temperatures, they happen very much more rapidly. Okay, so that's ignition. The other important ingredient to get to complexity and to us is to have segregation of the different kinds of matter, so that you have chemical disequilibria that get relieved by chemical interactions powered by this energy coming from the star, in our case, the sun. So it sounds paradoxical at first sight, but it's true that geophysics is more complicated than cosmology. This is actually a recurring theme that I find quite amusing, that less can be more. So you might think that since the Earth is part of the universe, the history of Earth has to be simpler than the history of the universe. However, sort of the standards of detail are different. And if you want to, if at low resolution, understand the universe, that's a much simpler task than understanding at sort of the Earth-like scales what the structure of the Earth is. And we saw a dramatic example of this last time when we saw that in two-dimensional materials, the quantum mechanics of anyons can be much richer and carry more information than the quantum mechanics of particles in 3 dimensions. And there are many such examples. Anyway, the gas cloud that condenses by gravitational instability and ultimately makes the solar system mostly winds up with matter in the middle, making the sun. However, some is left over, and that makes planets that don't have their own energy source, but are nicely powered by the sun, and of course, including and have different levels of irradiation depending on how far away they are. And well, there's a very complicated story of how stellar systems get formed. It's a very, very interesting story now at the frontiers of physics, because people have only in recent years developed the technology to observe solar systems other than our own. But now there are thousands of planets outside our solar system known in different systems, and the James Webb Telescope will be adding to the list substantially, and also telling us more about their properties, because you can do spectroscopy on their atmospheres. Okay, but as the materials form, they form very hot because there's a lot of gravitational energy released as materials form. Also, in the environment, you don't start neatly with planets. You start with a tremendous array of rocks and things like that, which gradually collide with each other and agglomerate, and that heats them up too. So the planets of any heft tend to be start off liquid, and the heavier substances in them tend to go towards the bottom. It's a very complex story because there's also chemical reactions going on, but there's a process of segregation that leads to an interesting layer on the outside. certainly in the case of Earth. And that leads to the next level of complexity. What I want to emphasize is that each step is something that you can understand scientifically, at least in broad terms. There are many, many rich details of the observations. There are many, many loose ends in these explanations, but sort of if your standards are low enough, you can see how it's all at least conceivable. And that's what I'm trying to get across today. And as you dig deeper, you find that this broad sketch actually holds up. So let's talk about how life got complicated. So as part of this segregation process in the young Earth, there were volcanic eruptions because some of these materials wound up in places they shouldn't have been and had to boil up. Some lighter material got somehow swept up down into where it shouldn't be, so it comes back up. Those are volcanic eruptions, and again, there's a lot of friction involved, so the dissolved gases in there get released, and that is basic mechanism where you get some rather rare materials in the universe as a whole. Carbon especially is quite rare in the universe, coming out on Earth. Enrichment by space debris, the comets and meteors that were left over from the formation of the solar system may also be important in adding materials on the outside where it can do some good for life. Anyway, the biosphere, this little layer of atmosphere and ocean and land surface that supports life as we know it, is not very impressive as a physical object. Let's go back again here. In this picture, which, by the way, is not drawn to scale, you see the radius of the Earth as a whole is about 6,400 kilometers. Most of it is these more or less homogeneous, these various minerals. It's only this thin layer on top and the crust, which is, as you know, just measured in a few kilometers. The mountains on Earth and the depth of the sea coasts and so forth is really only a few kilometers, and the atmosphere thins out very, very rapidly above a couple of kilometers. So this is a tiny, tiny piece of the Earth that we live in, and that's, as a physical object, so to speak, in terms of how much mass there is, it's not impressive at all. But it supports complexity, and that's why it's especially interesting. As I said, there are many, many open questions in filling in the details. One that I found particularly unnerving and interesting. So if you're looking for something to look into, this might be a promising one. The origin of the Earth's carbon remains quite poorly understood. There are debates about how much it came from volcanic eruptions and when, or maybe a lot of it came from carbonaceous chondrites, which are a kind of meteorite, or that also adds some carbon even today to the Earth. Okay, so those are kind of the ingredients and the power source for uh, or indications of the ingredients in the power source, let's discuss in a little more detail how these come together to manufacture complexity. It's really at the level of fundamental physics where we try to indicate what's conceivable. Chemists tell us what's realistic, and then biologists tell us what actually happened in this domain. But for physicists, if we just want to know why it's conceivable, I think the picture is quite compelling and remarkably simple. It's a simple tale of how complexity emerges. It's a tale really of two temperatures and one energy. Okay. The temperature characteristic of the biosphere that is roughly 300 degrees Kelvin. That's room temperature, if you like. So plus or minus 20 or 30 degrees is about as much as life can stand. So, but this is a typical temperature. The energy of a chemical bond, typical chemical bond, of course, chemical bonds are all over the place, but a typical covalent chemical bond is on a scale of an electron volt, which if you translate it into the temperature at which energies of an electron volt are in play is 10 to the fourth degrees Kelvin. So formally, actually, temperature has the same dimensions as energy. If you put Boltzmann's constant equal to 1, or use Boltzmann's constant, you can translate energy into temperature, and this is how they compare. And the temperature at the solar surface is 6,000 degrees Kelvin, and that's the temperature of the light emerging at Earth. So what you see is that the chemical bonds can be stable against most kinds of thermal agitation. So they have a kind of stability, but if they had absolute stability, things would just get stuck or be frozen. It wouldn't be life. Fortunately, there's a source of energy that's giving us high quality, although small in amounts, high quality extra radiation, extra energy that is capable of breaking chemical bonds. In fact, it's so capable that we sometimes have to put on sunscreen and so. But so it's on the edge of disrupting chemical bonds, which is what you want. You want to be able to, if you want complexity, you want things that are reasonably stable, but not too stable. So you can arrange them in complicated ways. They'll stay that way, but not forever. You can still manipulate them. You want things that stick, but aren't stuck. And that's what this kind of 3-scale reality gives you. Now, in more detail, slightly more detail, one learns that organic chemistry is the chemistry of carbon. So really, really complicated chemistry that's kind of open-ended. And the chemistry that supports life is based on carbon. What's so special about carbon? Well, two things. First of all, carbon is happy to bind to itself in different patterns. Okay, it has a valency of 4, so it can bind to several different things, either to itself. It's also fairly happy to couple to carbon. It can also bind to other things, but less strongly. And it's important, it's vitally important that carbon binds to itself, and this is what really makes it very unique, say compared to silicon, is that it binds to itself more strongly than it binds to the other available elements. So carbon can form long chains and intricate chains and rings that are stable. Okay, so it's a combination of the fact that it has 4 electrons available for bonding, and they can be in different geometric patterns. And it's a fascinating subject in chemistry to track that down to the basic quantum mechanics of electrons and Coulomb's law, but you can do that. And that gives you possibilities of branching, of forming rings, and getting to organic chemistry. Okay, so that shows, I hope, that the complexity characteristic of the world that we see, and in particular, the most outstanding example of complexity, life, and is something that is not only consistent with physical laws, but something that very plausibly emerges out of this simple star equations and simple star initial conditions. Now I'd like to, in the last part of this lecture, talk about a key mechanism that produces, this is kind of poaching on biology, so now I'm going to talk about what actually happens, but it also is important, I think, for the engineering of the future, as I'll elaborate. And it's just interesting. It's an important part of the world. So I'm going to talk about the theory, the phenomena of self-replication with variation, which to me is the secret of life. So first, let me say a couple of words about the power of exponential growth, which is what self-replication powers, because if you can have one guy becoming 2 and each of those 2 can become 2, then you have exponential growth. But that's also how numbers work in decimal notation. You start with a digit, and then you add another digit, and you have the product of their complexity, and you get exponential growth there too. Specifically, and this is a general mathematical phenomenon, so it's really even more basic than physics in a way. It's in the nature of Platonic reality, if you like, that, or logic, that if you combine things that have a simple alphabet, they could be the digits of the decimal system, or they could be the zeros and ones of the binary system, or they could be the ACGT of DNA, if you make sequences of them. Very, very modest sequence sizes translate into enormous numbers of possibilities. That's the combinatorial explosion, which is the key to a lot of what's going to follow, and is the key to making complexity. When you have choices among many, many, many possibilities, then which one you choose is encoding a lot of information, and that's clearly closely related to the possibility of getting things to be complex, things that need a lot of description, that take a lot of information to describe. Those are the things that are complex. Okay, so here's an example: a 64-bit register, which is L equals 2 things to choose, 0 or 1, and you choose 64 times. gives you this incredible number of possibilities. So mind-boggling. This somehow seems more intuitive because we're all familiar with decimal notation, but of course it's just the same thing as saying 2 to the 64. But somehow seeing all those zeros gives you an impression of just how gigantic the number of possibilities are. It's yeah. So if you translate it into dollars, it makes Elon Musk look like a piker, and also even the national debt looks small. Is small by comparison. But okay, in view of time, I won't elaborate on this wonderful, famous story of, well, I guess I am elaborating, of the inventor of chess, who was asked by the king, who was so delighted by this invention, to ask for a gift. And the inventor said, well, what I'd like is 1 grain of rice on the first day, and then 2 grains on the second day, until we fill the chessboard. And the king said, are you sure you want something so paltry? But you see, it does look very paltry at first, but it soon gets out of control, and the king realized that he was going to be humiliated by not having enough rice, so he killed the guy. That was his solution. But this shows you the power of exponential growth. And here's this is a handy thing to know, and also impressive for. So this is the chessboard parable, which is also the parable of the 64-bit register. That this is how many grains of rice or how many different possibilities you get on the 60 after you got 64 doublings. This is a very handy mnemonic if you want to change from binary to decimal counting. So and this one is how to get the number of cells in a human being, which is about 10 to the 12th, by cell divisions. You need about 40 stages of self-division. So this astronomical seeming number, which supports extraordinary complexity, given the power of exponential growth, only requires 40 stages of division. Now, in order to get a human being with different cell types and differentiation, you need to have variation as these divisions are occurring. And that's, so putting together those two ideas, self-replication and variation, is very powerful. So let's start with evolution, which is also embodies that feature. Self-replication with variation is the key to evolution, according to Darwin, as later informed by Mendelian genetics. You have the possibility of a generation of organisms reproducing several copies, but the copies are not exact. And so you have self-replication with variation. And that can be a good thing, as Darwin, and this kind of iconic, this is Darwin's finches that started from a small number of birds that somehow got to the Galapagos Islands from elsewhere. And then in the different islands, they found different environments and evolved accordingly so that they could eat insects on islands that had a lot of insects, or if the insects hid in trees, they could become woodpeckers, or if it was more promising to eat seeds, they developed the appropriate kind of beak for that. by selection. Now, in this case, you're sort of turning imperfection in the self-replication into an advantage, because it allows the organisms to adapt to different environments over time. The level of sloppiness is a meta variable that can itself evolve. Okay? If things are changing rapidly, you may want to have a lot of variation. If not, if things are easy, you can use the successful strategy that's already embodied, and that's kind of poetic, and it's actually realized by heat-sensitive bacteria and other organisms that adapt their level of variation to environmental conditions. Higher organisms are more sophisticated. They use sexual reproduction, so it's not just sloppy reproduction, but controlled variation in the replication. Sexual reproduction is a lot of trouble, and I'm not talking about social problems, but the cellular mechanisms are quite complicated, so there must be some big payoff for this. Here's a rough indication of how the things work at the cellular level, and the key thing here is the possibility of crossing over. So the child gets contributions from both the mother and the father, but gets pairs of chromosomes. And what can happen at the crucial stage of mitosis, when the egg forms, is that you can trade pieces of chromosome. This is called crossing over. And then the child gets a mixture at the molecular level of its parents. And the big advantage of this is that crossing over takes whole big chunks of chromosomes. So if you think of a computer program, you don't want to sloppily change single lines of code. That's a kind of disaster. But if you do big chunks in a controlled way, then you can have something that still works. Also, if you have backup chromosomes, if you have double, you can experiment and still have one copy that still works. So it's more redundant. And then finally, you can use sexual reproduction allows more refined fitness criteria, because the organisms themselves can look for desirable features in their mates. So you can also test out the phenotype in that way. So that's an important refinement. Okay, so that's how a very broad indication of how self-replication with variation is key to evolution. The very same thing conceptually is the key to development. So I already alluded to the fact that you start with an egg cell, it doubles again, doubles again, doubles again. 40 times is enough to make a human now. And the first few cycles are actually all synchronized before any big specialization happens, and sort of literally like that. But there's controlled variation because there are chemical gradients that change or induce changes in the DNA that program the cells, and you start to get different kinds of cell as a result. This is called epigenetics. So you start with just one program. Well, this is showing again how different numbers of doublings give you the growth of the embryo. But okay, you're still using the paternal and maternal genetic material to make all these different kinds of cells. And the way that trick is done, this controlled self-replication with variation is primarily by what's called epigenesis, which is now something that biologists are beginning to understand in detail. That is, you can modify the DNA by adding methyl groups or by, well, the DNA gets wound up inside the nucleus. It's a DNA molecule unwound would be 6 feet long, which is much too long to fit into most bodies. It certainly would be inconvenient. So it gets rolled up and you have to unroll it, but you can control which parts get exposed in the unrolling and translated by putting on these histone, there's histone modifications that sort of hide different parts. This methyl group also makes different parts of the code inactive. And so by these kinds of modification, you can have the same sort of underlying code representing different programs for different cells. So you can get self-replication with highly controlled variation this way. And that's the key to development. And finally, the other great trick that this does for biology is it's the key to maintenance and repair. Okay? Once you've made the embryo and a young organism, and it of course goes out into the world, it gets things wear out, it gets exposed to various insults and dangers and cuts its finger, and so you have to be able to repair. Now the mechanism of that is again self-replication with variation. You have a certain so-called stem cells that are close, are not as differentiated, so they have relatively little methylation or histone modification. They're sort of closer to the egg, so to speak, and in response to need, they can generate, they can double, and with one of the the children being different because of epigenetics, renew the needed cell supplies. And in case of injury, this whole system gets called into play using chemical signals that get emitted from the injured region. So self-replication with variation is an enormously powerful strategy for leveraging the power of combinatorial explosion. Remarkably, and to me, a great opportunity for the future, this idea is currently very, very little used in engineering. The idea of self-replicating machines with that have programs that vary, so that they don't just reproduce themselves, but reproduce with variations in controlled ways. And let me just end this lecture by having some fun and speculating about the sorts of things you might envision doing if you could implement that kind of engineering. So one is, remember, you can start small. Exponential growth very quickly can give you a lot of stuff. We've experienced that, of course, recently in the pandemic. That started out as a small thing, and a few, maybe one monkey in China, and then became a worldwide phenomena that's plaguing us even to this day. A professor at ASU, it turns out, Professor Lackner, was a pioneer in thinking about these things, and his vision, which might be a very important one for the future, is that you would have self-replicating machines that would be sort of little self-replicating factories that would produce solar panels. So if you want to make lots of solar panels and make the desert into a source of electrical energy, self-reproducing machines that could do that would be a way of making solar panels that cover vast amounts of area. Science fiction writers have carried this even further, talking about terraforming the entire Earth. If climate change really gets catastrophic, we may need to do projects like this. One that particularly intrigues me, and I think would repay further study, is that, and because it's closer to biology, so it's really we have the self-replicating machines in a sense, is that algal blooms of algae, have significant effects on weather and climate. Okay, you get blooms of algae, which are usually thought of as a nuisance because they change the weather and can even change the climate in the ocean. If you can control those things, you can change the weather and the climate in ways that you like. So we're going to turn bad news into good news, maybe. This is just a picture of not only terraforming the Earth, but science fiction authors have dreamed of terraforming Mars. And I guess Elon Musk would like this. You could turn Mars into a user-friendly planet. It's a, yeah. And to me, if you don't do this, then going to Mars is not a great idea. Another great project that could be contemplated using this engineering of the future was also considered by science fiction writer Olaf Stapledon, who I very much admire and recommend to your attention. And he envisages the long-term history of humanity, and they call them the different men. We are the first men, but then in response to different cosmic calamities and opportunities, the human race evolves in different ways. And the fourth men are the giant brains. The third men are these creatures that become very good at genetic engineering, and then they decide what they need, but somehow they're not intelligent in general, and then they decide they need guidance from giant brains and engineer that. The point is that I don't think it's so unrealistic. The human brain has a very stereotyped architecture, and it evolved from much smaller brains on a time scale that by the normal standards of evolution was quite short. So probably involved a rather small number of genetic modifications. And so as we learned, that can be done again. In fact, the limitations on human brain size are largely the fact that, well, two things. First of all, brains are very metabolically expensive. They use a lot of energy compared to other parts of the body. Uh, Secondly, it sounds, I mean, uh, uh, it's not clear that high intelligence is an advantage to survival or in evolution. It's only arisen very, very rarely in the natural world. In fact, here on Earth, at most one time has intelligence, high intelligence emerged. Uh, However, it does seem that uh, the limitations are, first of all, that it's expensive. Secondly, that it doesn't do you necessarily much good until you pass a certain threshold. And then thirdly, it's anatomically difficult. It's very, human childbirth is very, very difficult because the heads are so big. But of course, if you're engineering it, you could, you know, engineering giant brains, you don't necessarily have to uh, produce them in the same way. They could be free floating in the ocean or whatever. And then finally, I'll mention one more kind of project that's closer to physics. The energy released by the sun, that's potentially very useful in producing complexity and might be something that a sufficiently advanced civilization would want to exploit, mostly goes out into empty space. Okay, we talked about putting solar panels up, but solar panels by this are still going to capture only a very, very small, subtend only a very, very small spherical angle at the sun. If you want to capture all that energy, you have to make a gigantic thing. That's called the Dyson sphere. And if you want to make a Dyson sphere, the only way you're going to do that is by having machines that self-replicate and use the power of exponential growth. And then the last, whoops, I don't want to show the movie because we're kind of, there's not time for it. I'll show it maybe in class if someone's interested. Von Neumann probes are I think the only remotely realistic way of exploring the whole galaxy. They would be units that travel out, self-replicate, and could form an expanding cloud of objects that send back information, communicate with each other, send back information. And over the course of times, which are very, very long compared to a human lifetime, but very short compared to cosmological times, a few tens of thousands of years, you can, working at realistic sublight speed, you can start to imagine that these probes would expand through significant regions of the galaxy. And over a few million years, which is still short compared to cosmic scales, you could explore a lot of it or settle a lot of it. Okay, so before I learned about this concept and convinced myself that it was not completely nuts, I thought that the idea that we've been visited by alien civilizations was extraordinarily far-fetched. I still do, but I think it's conceivable, at least. However, I think these von Neumann probes would not take the form of humanoids stepping off flying saucers. They'd probably be very non-intrusive little things that are not just meant to gather information and self-reproduce. Okay, finally, I'll very briefly start with I talked about some wild stuff, including things that you'd want to think very, very carefully about before attempting if these technologies actually come to pass and mature. As became famous in the Spider-Man films, with great power comes great responsibility. And, uh, there's a marvelous part of Fantasia called The Sorcerer's Apprentice, in which Mickey Mouse, who's the sorcerer's apprentice, learns how to do a magic trick, which leads to self-reproduction of a broom. And when he's asked by the master to clean up, he makes use of this. But his skill in magic gets out of hand, and these guys become an army that do things that he's not really prepared for. And I'll end with this guy. This was a use of a form of self-replication to try to solve a problem that got out of hand. This creature is called a cane toad. Cane toads were introduced into Australia in order to eat some insects that were causing difficulties in the sugarcane crop. It turns out that they weren't very good at eating those insects, but they were very, very good at self-reproduction, and they've overrun Australia. And if you want to see some very entertaining, although distressing, case studies in a very entertaining case study in self-replication gone wrong. Look up cane toads on the internet, and you'll find this ongoing crisis documented. They're taking over the Australian fauna. Okay, so that's what I wanted to say in the lecture. I hope I've convinced you that we can understand in a broad brush way, but also in powerful ways that give non-trivial insight into our world, how things started from very, very simple, very definite prescriptions and became something like, and in fact, presumably the world that we experience. Thank you. Now we'll go upstairs. Are there any? Yeah, we had one question. I don't know where it came from, and it's a very general question. I'll just quickly address it. How do we convince people disconnected from science that knowledge creation, discovery is itself progress, and that theoretical knowledge is, well, let me just summarize the question is, how do we scientists, as scientists, share what we've discovered so that people can benefit from it, but also appreciate its value and not resent it if they're taxpayers that are funding science, for instance, or maybe they even want to contribute. Maybe if they're undergraduates at Harvard, they might consider whether to become scientists instead of financiers, for instance. So how do we do? Well, I think we have marvelous tools now for reaching out on the internet, and I view it as an important part of my job to be giving lectures like this that are going to be recorded and distributed, and that really try to convey the material in a way that people can digest without going through 8 years of training, undergraduate and graduate, in order to get to the frontiers of knowledge. Because I think you can convey in a meaningful way the frontiers of knowledge, and that when people see it, they will appreciate it. You can also point out, as I've been at pains to do, that the technologies that drive modern life came out of fundamental research. Okay, there was fundamental understanding of the quantum mechanics of materials, and semiconductors in particular, but that enabled gizmos like this or this to be manufactured. Okay, so that that if scientists got 1% of the money back from the wealth that's been added by fundamental research, it would be more than we're currently getting, and it would pay off handsomely in future wealth as well. So I hope that answers the question.